Hello everyone, welcome to lecture 1, video 1, and in this lecture we are going to cover something that's known as overfitting. It's a very important aspect of machine learning, and that is what we are going to talk about in this lecture. More specifically, what is overfitting? How do we define it? Is there a measure that we can utilize to quantify it? And cases or situations when it occurs? And then there will be a discussion on the difference between stochastic and deterministic noise. Okay, so even before beginning with the topic for today, let's quickly review what we did or quickly recap what we did in the previous lecture. So in the last lecture, we saw an illustration of how we can use nonlinear transforms to deal with data that's not linearly separable. So here you can see that this wasn't linearly separable. What we did was we utilized a transform, which is nothing but a function. And that function essentially mapped the same data to another space, which we called the Z space. And in the Z space, as you can see, we could linearly separate the data somehow, depending on how we did the transformations. For example, in this situation, we kind of came up in, like, if we try to visualize what we did was that in the original space, we managed to get a non-linear boundary. And under the hood, what was happening was these two things here, and this is the linear separator eventually. And once we had the final hypotheses in the new Z space, we were able to translate that to the original space. So basically, whenever we have a new point, right, under the hood, as I said, we will have a linear model, which is here. But on the client side, or if you're like working with some data, then you know that if a point lies here, that means it maps to this region, and so this is in this red area. And if a point lies somewhere here, you know that it maps to this, and so this is the blue area. And that's how we learned about this nonlinear transformation in machine learning, which is an important aspect because obviously we don't have data that we would like to have, so we don't have linearly separable data all the time. Okay, so having said that, let us look at this one more example where we saw this was the digits data, right? And we use the linear model, and here we use the third order polynomial. So this one is the linear model, this is the third order polynomial, and we saw the difference between the E in and the E out, right? So although the linear model is showing us that it misclassified a lot of points essentially, and the third order polynomial took care of more number of points. So as you can see, it has a nice curve, and so could take care of like these points that were misclassified in the linear model, and we got a better E in and a better E out. But when we kind of compared both the models, we saw that there was like hardly a 1% increase in accuracy from this to this. Like after doing all the polynomial transformation, all that under the hood process that goes on, we came up with 1% improvement, which depends on what the problem is and where exactly are we trying to apply this. And so it could be really, really important. That 1% increase could be really important for a certain business, but for the other or some other application or some other business, it might not matter. So depending on the application, you need to decide whether you'll still go with the linear model or whether you'll go with a higher order polynomial. And again, it depends on the application, and linear model does, I would say, quite well in most of the situations. So again, think about whether your problem can be solved with a linear model. If not, is it worth putting all that effort to go into a higher order polynomial and getting that 1% like improvement in accuracy or not? So it's us who will decide like whether we select this versus this. Okay, so this was the last lecture, and now we are moving to something that's known as overfitting. And we saw a small like an illustration where we went overboard, and then there was this, like, we were trying to fit this really complex function, and we saw that E out wasn't as impressive as we would like it to be. And so that's where the idea of overfitting comes from. And if you think, like, generally humans have this tendency to overfit, right? So we have these superstitions based on, for example, the fear of Friday the 13th, right? So in general, This is like an example of humans' ability to overfit. And like maybe some unfortunate events happen on this day, right? And if you think about it, like unfortunate events, it's equally likely that an unfortunate event can happen on any other day than Friday the 13th. But then unfortunate events are memorable, and given a few such memorable events, it's natural to try and find an explanation and say that, okay, Friday, whenever 13th comes on a Friday, there is something bad that's going to happen, right? So, overfitting is actually the phenomena where fitting the observed facts, which is data, no longer indicates that we will have a similar thing in the larger population, right? So maybe it might lead to an opposite effect, right? So overfitting is something that can lead to an opposite effect of what we are really trying to do. Okay, so let us begin thinking about what overfitting is. And we begin with using this example, this really nice example where we have like 5 data points, right? And the target function is quadratic. So this blue line is the target function. And we have 5 data points and some little noise has been added. So notice they don't lie exactly on that like quadratic function, but when we were measuring the data or whenever the data was generated, a little bit of measurement error occurred, and that's there, right? So you can see like this point is a little off, this one and so on. Okay, having said that, um, the target function is given to us, and so this is like more of a like an illustration of what might happen, right? So this is like, let's consider that this is like a one-dimensional regression problem where we have like x and then this is my outcome y, right? And only 5 data points. And let's say that we are trying to use a general model and maximize our chance to capture this target function given the data, right? So I just have the data, I don't know the target function, and so I'm going to utilize that and maybe fit a function. Okay, so what function do I want to fit? Here, what I did was I fitted this fourth order polynomial. Okay, fourth order polynomial. Why did I do this? Well, there are 5 points, and from our basic algebra knowledge, I can say that I can fit these 5 points like accurately by a fourth order polynomial. So that's why I selected a fourth order polynomial. Well, the result is shown in this picture here, as you can see. And this is like a classic example of overfitting, because the target function is a quadratic function, the blue curve, right? And with a little added noise in the data points. Now, the target is way simpler, and the learning algorithm utilized the full power of a fourth order polynomial fit, like as far as it could go. It just went ahead and did that, right? But the result does not look anything like the target function. I mean, this curve here, this red curve and this blue curve, they are like really far apart. If you just look at the picture and just like not look at the data points, right? So this is a classic example of overfitting. The little noise in the data actually has misled the learning. Why? Because if this was like something like this and the data points were exactly on this with no measurement error, then I could have come up with like a second order polynomial that would have like exactly fit the data, right? So the little noise has misled us, because if there was no noise, then the fitted red curve would exactly match my target. This is a typical overfitting scenario in which we used a complex model and used its additional power, the degrees of freedom to learn the noise. So if you think about it, I've really learned the noise because I really wanted to like go capture every intricate detail here of the noise and not the target function. And so one outcome of this scenario could be that, of course, here my E of n is going to be 0, I would say, because it has exactly fit the sample that I have. But then what will happen when I'm trying to generalize? As you can see, most likely when I'm trying to generalize, because my target function is a quadratic function, my E out is going to be huge. So one likely outcome when we are overfitting is bad generalization. Bad generalization in terms of how we perform outside of our sample. Okay. Now, the definition of overfitting, so let's define what overfitting is. This was just an illustration. So the definition of overfitting is to fit the data more that is warranted. So this not only includes bad generalization, it also includes the bad, I would say, like, in fact, it's a process, I could say. So also the process of picking, the entire process of picking hypotheses with lower E in, resulting in a higher and higher E out. It's the process of picking a hypothesis with lower E in, resulting in a higher E out. Okay, so let's look at this quick example to understand what is this process of picking a hypothesis with the lower in and why is it resulting in a higher and higher E out. So if I just like go ahead and plot this thing, this relationship, and let's say this is my overall error, right? And this is my VC dimension. And if you remember, for the in-sample error, this is going to go down and down. As I increase the VC dimension, the power of my sample within like calculating the error for the sample increases because I have like a higher VC dimension, right? And what happened to my model complexity in terms of and the overall E out, if you remember, was something like this, right? So this was my E out. And so we were doing fine until this point. So this was my optimal point. And so we are fine in this region, right? In this region, we are fine. And it is here, this is my overfitting region. So conceptually, whenever I lie in this region or my model lies in this region, this is when I tend to overfit because I'm going further and further apart from my E out. I'm selecting my hypotheses in such a way that I'm focusing only on getting my E in as small as possible, and that is making the the binding relationship between E in and E out to go loose. And so I'm lying in this overfitting region. So this is like what conceptually we are looking at. Okay, so to illustrate further, we have a case study where we are looking at overfitting with polynomials. So let's look at this. So this is the case study where the blue curve is the target function and we have some data. So this is like case number 1 or A maybe, and this is B, case A and B. The target function is 10th order polynomial, but this one has noise. So A has noise, as you can see, and B has no noise at all. Okay, and what are we exactly trying to do here is that we will try to come up with a hypothesis, right, to fit both of them and see, or maybe come up with like two hypotheses. Why not I write it, like what exactly are we going to do? So let me try to come up with, like, I have this choice of hypothesis sets, right? Let's say I have like two choices. So one is the second order polynomial and I am denoting it by h2. So this is like second order polynomial. And then the other one is the 10th order polynomial. So just like I'm writing 10th order. Let's say this is the choice of my hypothesis set. And how do we get these? Well, just get the appropriate order polynomial transform. For example, for h2, excuse me, for h2, if I have like, this is like one-dimensional data that we're looking at, right? So for h2, the input is 1 and x. And so with the transformation, I'm going to get 1 x and x squared, right? And similarly for h10, again, I have 1 and x. I'll apply the feature transform and I'm going to get 1 x, x squared, and so on, all the terms up to the x 10th power. This is how I'm going to get these hypotheses. Okay, now we have to pick one of the hypothesis sets depending on the problem. And so the question is, which one should we pick and why, right? So let me like write it in a tabular form. Let's say this is my target function where my f is 10th order with noise, right? And F is 50th order, it's quite complex, and no noise. Okay, and these are the choices of my hypothesis set, H2 and H10. Which one should I pick? If you think about this, like if I'm in this box up here, top left, and then the noise is there, and so the noise might create a lot of issues if I'm selecting the second order polynomial. And so because the noise will not let me completely model that, so maybe I will not select this one, right? And instead, how about the 10th order polynomial? Now there is noise, I agree, but then this is also a 10th order polynomial, and my target function is also a 10th order polynomial. And so maybe I'll pick this one, right? What happens to this second target function, which is the 50th order, and there is no noise? Well, if I'm trying to fit this second order polynomial here, I don't think I'll come even like close to this. So I don't think there is any hope of coming close to the target function. And so I would just discard it. The 10th order is, of course, a little more, it has more, I would say, dimensions to it in the sense that it's more complex. And so maybe I will select this again because, of course, this is not exactly 50th order, but then it's complex enough to get the intricacies of everything. And just like a word of caution here, we are, of course, synthetically generating data. We can never know the target function, but just for analysis sake, we have the target function in front of us, and we just are trying to understand what happens. So let's see what happens. Okay, so we've decided that we're going to pick H10 in both the cases. So here is an illustration, again the same data. This is like case A, and this is my case B, right? And by the way, let's assume that this is my simple learner, because this is a simple model. So this is a simple learner, and this is a complex learner. Okay, so my simple learner is my second order fit, which is the green line. So green line is the simple learner, and 10th order is the complex learner, which is my red line in both the situations. And if we just like go ahead and look at the outcome, right? My plausible reasoning for my hypotheses, my H2, my simple learner, was bad in both cases, as you can see from the results. So basically whatever I said here, whatever I decided that I'm going to like discard H2 in both the cases was wrong. And in fact, H10 was the bad choice. And it is so counterintuitive. It is surprising that why the simpler model is doing better in both the cases. And just like to emphasize, this is my simpler model, this is my simpler learner, and here is my simple learner, and this is the E in and the E out. You can see that the 10th order, my complex learner, really gets like my E in like 0 almost. But then see what happens to the E out. It is a disaster in both the cases almost, right? Now, what happened? What really happened here? Well, we know that the target function in this case, in the first case, is a 10th order polynomial, right? And it's possible for my 10th order polynomial to overfit, which is what it's doing here, the red curve, right? So we are better off ignoring the knowledge of data being 10th order, and we are better off using the simple one, the simpler model, because we have measurement error in the data. We have the noise in the data, and that noise is making this, like the more complex model, basically go really haphazard, in the sense that it is, if you think about it, like in both cases, the 10th order polynomial heavily overfits the data, and it's resulting in a nonsensical final hypothesis, which does not resemble the target function. But then we can argue how come the second order, because obviously it's that is also not like coming close to the target function. So of course it does not capture the full nature of the target function, but it at least captures its general trend, resulting in a significant lower out of sample error, which is what we are seeing here and which is what we are seeing here. So that's like a case of good generalization. Okay, so that's the first point. Now, what happened here? What happened here? There is another aspect to this one. This was, remember, the target function is the 50th order polynomial. with no noise. So here, when there is no noise and f is, let's say if f was 10th order polynomial, right, then our intuition would be that the 10th order would be a perfect, like it would capture the entire, like the intricacy of my target function. But if we go on increasing the complexity of f, which is the case here, right, we have the 50th order case here. What will happen is, even without noise, because of the increased complexity, you have to decrease the complexity of the learner, because you don't want to overfit, because even a small up and down, right, in the target function can result in a huge, like, change in your hypotheses. So basically, in practice, what's happening is, like, here we can say, okay, why don't I go and use the 50th order polynomial? And is it, again, like, another question that arises, is it that the second order is order polynomial, or the simpler model is always going to do better? Well, not always. For example, if the data was noiseless in this case, and or maybe in this case rather, the data was noiseless and it was a 10th order polynomial, as I said, the complex model would have fit really well, right? But in the 50th order polynomial, although the data was noiseless, right, overfitting happened. That resulted in a bad E out. Now, the to summarize what's going on is that what matters is how the model complexity matches the quantity and quality of data, because we don't see the target function. We only see the data. And so what your algorithm is doing is essentially trying to fit the data and not the target function, right? So this is what we see: simple F with noise, complex F with no noise. So basically, my hypotheses should try match the quantity and the quality of data and not F. And because of the way the data is distributed, or the way the data is given to us, a complex model is more likely to go nonsensical and not generalize well outside of this sample, because obviously if I have a complex F, it's hard to learn even outside the sample, right? That's the intuition behind this idea of overfitting. Now, we've talked about the intuition of overfitting until now, and what we need to understand is, can we quantify it? And if we can, how is that? So that's what we are going to look at in the next video.